Hello friends, it's my pleasure to meet you once again. In this video today, I'll be carrying you through to how we apply chi-square in carrying out tests of hypotheses. We'll be using chi-square to carry out tests concerning more than two population proportion. This test is also known as test of homogeneity, and sometimes contingency test. The word homogeneity simply means we are trying to test the opinion of people whether it is the same or different, whether what people feel about a particular matter is equal, or whether their opinion differs. That is the idea of tests concerning more than two population proportion, also known as homogeneity test. On the board here, I have a question we're going to use in carrying out this test. Please come along, let us read this question and see. We have a table there. The table shows the opinion of some students drawn from three different schools, Unizik, Okopoli, and Futo. We have those in favor of a particular motion. There are others against that motion. These are the people and the responses given, So we want to read through the question and see how we use chi-square to carry out this analysis. The table above shows the results obtained from students of three post-secondary institutions in eastern states of Nigeria on whether the rush in academic activities in the first phase of post-COVID-19 should be continued. Tests at 0.01 significance level if their opinion differ. So that's our interest. We want to find out if their opinion differ. Now, how do we do this? Look at the question, you notice that we're given the significance level, which is 0.01. That significant level is the same as 1%. 1%, 1 over 100 will give you 0.01. So that value, we call it the significant level. Before I move on to talk about the degree of freedom, I want to state that this significant level could also be in confidence coefficient. Confidence coefficient is 1 minus alpha. I stated this in one of our previous videos already placed. You can search through our YouTube channel to watch that video when I said something about significant level and confidence coefficient. For example, this 0.01 or 1% significant level corresponds to 99% confidence coefficient or 0.99 confidence coefficient. So that depending on whichever chi-square table you're using, you would know what you're talking about. Depending, you know what you are looking for there. Okay, now the degree of freedom, C minus 1, is 3 minus 1, which is equal to 2. How did we get the 3? It's simply the number of columns. Is that okay? So whenever you're carrying out test of homogeneity, test concerning more than two population proportion, your degree of freedom is simply the number of columns given to you, minus 1. Now with these two values, significance level and degree of freedom, we can get the tabulated chi-square value. Because all we do when using chi-square to test hypothesis is to compare the value of calculated chi-square and tabulated chi-square and check which one is greater, which one is less, to help us now to make a decision whether to accept the null hypothesis H0 or to accept the alternative hypothesis H1. So quickly, I would get my chi-square table and then we would check for the value of chi-square tabulated, which I wrote 9.210 here. How did I get that? From these two values. These are critical values. So I'm going to reach out for my table, show you my chi-square table. Alright, this is what it looks like. This is a chi-square table. Okay, so we're going to use this table to obtain the tabulated chi-square value corresponding to a degree of freedom of 2 and significance level of 0.01. In my table, this table is constructed in significance level, not confidence coefficient. In subsequent video, I'll be telling you what you should know about chi-square table in case you lay your hand on one that is given in confidence coefficient. Alright, so let us see what we do there. Now this is the table. You will observe that you have a column which is degree of freedom. You can see it here. Then your significance level, we have it here. Now our interest is degree of freedom 2. So let me highlight it. Degree of freedom 2. I've highlighted it. I hope you can see it. Then from our question, the significance level is 0.01, which I told you is the same as 1%. If you multiply 0.01 by 100, you get 1%. So the significant level, let me highlight it as well too. Pick our critical point of values of interest. So we are going to trace that critical value vertically, that is downward, following that column. Then we trace the degrees of freedom 2 horizontally, where this value of 1%, which is 0.01 significance level, and degree of freedom meet. The value there is our chi-square tabulated. If you do the trace, you would see, follow along this column, move through the degree of freedom 2 horizontally. The value is 9.21. Let me highlight. So you see the calculated chi-square from our table here is 9.21, subject to a significance level of 0.01 and degree of freedom 2. That is, of course, how I obtained the chi-square tabulated to be 9.210. Now, let us go for our hypothesis, because, of course, it is the hypothesis you're trying to test to know whether the opinion of this student differ or whether it is the same. Now, the null hypothesis will follow along with the statement on the board here. Are you following, right? The alternative hypothesis will be against the null hypothesis. These two hypotheses are always opposed to each other. So let us see what the null hypothesis is. On the board here, the null hypothesis is saying that there is no significant difference in their opinion. What does it mean? It means that the opinion of students from Unizik, the opinion of students from Okopoly, and those from Futo are all the same. So if maybe those in Unizik said, oh, the rush should continue, then it means it is the same with what the other students from Okopoly and Futo said. Even if from the observed frequency values we got here, it's not exactly the same per se. But you know, when carrying out test analysis, we actually draw from a population. We draw a sample from a population, analyze what that sample says, and then we can make some justifiable conclusion. That is what we do in statistics. And such conclusion, in most cases, at higher level of acceptance, would work out. It will work out. It's just in few cases that it may not. Of course, it may interest you that we use things like this to carry out stuff like fact checking, to check fact, what people say about a particular matter. Alright, let's just move on. The alternative hypothesis is saying that there is a significant difference in their opinion. You see now that is opposed to the null hypothesis. Null hypothesis says there is no difference. Alternative is saying there is difference. It means that their opinion is not equal. Their opinion differ. I hope I'm communicating. So we cannot just wake up and accept any of the hypotheses just from what we are seeing here. What we are seeing here is raw data. It's raw information. We need to analyze it. We need to make certain calculation and comparison before we come up with a justifiable statement. And that is why, to do that, we will proceed to obtain chi-square calculated. We need the value of chi-square calculated so that we can now compare it with chi-square tabulated. The comparison, and from what we see, will now help us to make a better decision on what to choose here, whether null hypothesis or alternative hypothesis. The decision rule in one of our videos, I've already explained it. So please, if you've not subscribed to GMAS41's YouTube channel, we appeal to you to do that. Subscribe, and once you subscribe, you see the notification bell. Press the notification bell, turn it on, so that once we upload videos, you would get personalized information or notification that we've uploaded new video. Having said this, friends, I will go for a short break. I'll be back so that we can calculate chi-square. When we calculate, we can now compare with the tabulated value, which is 9.210 obtained. But it pleases me to inform you before I return from the break that I'll be bringing to you the Omeka's beta epsilon chi-square factor algorithm or formula method of solving for chi-square calculated. Before the short break, we have already determined the value of chi-square tabulated, and we got 9.210 at a significance level of 0.01 and degree of freedom 2. It is now time we want to determine chi-square calculated and then compare with this chi-square tabulated. In order to avoid the stress of too much tabulation, I am pleased to introduce you to the Omeka's beta epsilon chi-square factor algorithm or formula which can be used to determine chi-square calculated. Alright, and here on the board we have the formula. This is the beta epsilon chi-square factor algorithm. The important thing about this formula is that you can still use it, alright, in a case where the table has more than 2 rows. This table you're analyzing is 2-row table. I created this total because we need to total some things in order to be able to substitute into this formula and get certain values. Is that okay? And now this formula can also help us to avoid any stress of tabulation. We'll just work with the table given to us. Now we're going to see how we apply this formula. Then in subsequent video, we will also work on the general approach of obtaining chi-square, going through constructed different tables, alright? For example, the table for expected frequency and the difference between observed and expected frequency. Until then, anyway, in this video, my interest is to specifically put you through this Omeka's beta epsilon chi-square factor method, because we really wish that you friends use it as you really enjoy solving problems on chi-square by this method. Before we go on into seeing what we solved here, there are certain things we need to know about this formula. First of all, the meaning of the OF sub 1 sub n, and even here OF sub 2 sub n, the meaning of CT sub n, the meaning of beta, the meaning of epsilon. And that I've defined here, OF sub in, where this I could be row 1, row 2, row 3. In this case, OF sub 1 means observed frequency of row 1. Then nth column, where nth can also be 1, 2, 3. So we'll talk about the observed frequency in row 1, column 1. Like in this table, that corresponds to 74. Because this 74 is in row 1, column 1. What about the observed frequency? Let's say maybe row 2, column 3. You come to row 2, column 3. The value is 57. Is that okay? So that's the meaning of the OF sub in, as the case might be. I've told you that n and I could take the value 1, 2, 3, where I represents the row, number of row that the observed frequency belongs to, and then n represents the column that the observed frequency belongs to. Beta here is chi-square factor of the first row, that is row 1. Epsilon is chi-square factor of row 2. Like I said previously, suppose we have more than 2 rows here, let's say 3 to 4 rows. It means we will write a formula similar to this. Here it will be plus, we'll write something very similar, OF3n minus CTn times chi-square factor for that row. I can choose to use something like gamma for it, put all of them in square, divided by the denominator, and it goes on that way. So this is actually a powerful formula. Is that okay? I would like us to get the value of beta and the value of epsilon, because we need them in this table, in this formula, rather this algorithm. We also need to know the value of the column totals for each column in the table there. That was why I created this extra row and column, so that we can be able to get our total. Let us do that quickly, because I actually use those values here. So how did we get the values that we substitute here? I'm going to work them out here so we can see. First, to get our beta, we need to take some totals, right? Let us go to the table and total some things. So we'll get row totals, we'll get column totals, and then at the end of everything, we'll take overall total, that is grand total. Row total, row 1, let's see, 74. 74 plus 70, then plus 23. So that's giving 167, right? It gave 167. So I'm going to write that 167. And then let's check our row 2, 24 plus 128 plus 128. And then we are adding it to 57. So it gave 209. 209. All right, let's check the column totals. Column totals, we have 3 columns here. So the first column 74 plus 24. So that gave 98. Permit me to use red colored marker. 98. And then 70 plus 128, column 2. So the total there is 198. 198. And then, of course, column 3 is 23 plus 57. The column total is 80. Now, you see this column here, this is the grand total box. Grand total box. The overall total of all this, 1, 2, 3, 4, 5, 6. The observed frequency given to us. Add everything together, you get this overall total, which we call grand total. But we can actually avoid all those stress. We've done all those additions. Now, if you add these 2 values, you get a grand total. Or if you add these 3 terms, you get a grand total. The choice is yours. Let me add 167 plus 209. I want to go across the column, or down the column rather. So that gives us a total of 376. I'm going to use black marker for it. So that's the grand total. That's the grand total. Is that okay? Under here, let me write CT1. CT2, CT3, that is column total 1, column total 2, column total 3, and then here I'm going to write grand total. Good. Having done that, let us now come back and obtain our chi-square factor for the first row and chi-square factor for the second row, beta and epsilon respectively. So to obtain beta, beta is equal to, remember that beta is chi-square factor for row 1. So it's going to be row 1 total divided by grand total. So I'm going to have 167 divided by 376. 167 divided by 376. Let's see what it's going to give to us. 376. So the value from here is 0.4441. 0.4441. Good. I will also get for epsilon. Epsilon is chi-square factor for row 2. So I'll go to row 2. It's going to be row 2 total divided by the grand total. Row 2 total is 209. 209 divided by the grand total, 376. And of course, the value given to me here is 0.5559 approximately. So it's going to be 209. 209 all over 376. Row total 2 divided by the grand total, 0.5559. So that's how we got the chi-square factor for row 1 and row 2. Of course, if this table is up to row 3, you're going to get a chi-square factor for row 3 simply from sum total of row 3 divided by the grand total. Now, all you need to do is go to this Omaca's beta epsilon chi-square factor formula and then substitute for the necessary data you have there. Solve with your calculator, present, you get your answer. And that's what we did here, okay? So let's quickly look at this. Let's look. Now, you notice this formula part is for row 1. So it's going to be observed frequency of row 1, column 1. I'll start with that. For observed frequency of row 1, column 1, if you come here, this is row 1, column 1 is this, and it corresponds to what? 74. So this part now will now become 74 minus, open bracket, column total for that first column. The column total is 98, you fix 98 times beta, the chi-square factor for row 1, and that value is 0.4441. Look at it. So I enclose all in bracket and then square. You can see that divided by column total of the nth column you're dealing with times the chi-square factor of that row 1, which is what you have here. A good thing about this is this part of the numerator is always what you have in the denominator. Is that okay? Now let us move on. Remember, this is summation of what you have in row 1 following this formula. So it's not going to be plus we go to row 1, column 2 this time around. Row 1, column 2, the value is 70. So follow this formula, it's going to be plus 70 minus column total of that second column, because 70 is in the second column and the column total is 198. You can say that multiplied by row total of row 1. We are still dealing with row 1. You can see the formula, okay? So row total of row 1 is 1, okay? Times chi-squared factor rather. Chi-squared factor of row 1, which is 0.4441. That's beta. You have the formula there. Okay, let me quickly jump to that of row 2. Let us see how we get this value of row 2. Let's see how we get this value of row 2. In that value of row 2, this is the first term in row 2, which, if you follow, is going to be observed frequency of row 2, column n. Of course, row 2, column 1. Move on, row 2, column 2. Row 2, column 3, according to the table. So we go, observed frequency of row 2, column 1. Row 2, column 1 gave us 24. So it's going to be 24 minus open bracket. You are following this formula now because you are summing along the second row. You can see the formula. So minus column total of the column you are dealing with. The column I'm dealing with, where 24 falls in, the total is 98. So it's going to be 98 times chi-squared factor for row 2, which is epsilon. We have the value to be 0.5559. So look at that. 98, column total for column 1 times epsilon, chi-squared factor for row 2. Square it and divide by that same term in bracket in the numerator, you bring it down. Let's go to how we obtain the last value here. Alright, the last value. Of course, that will correspond to this, because the last value is row 2, column 3, the observed frequency there. So you follow this formula again. Observed frequency of row 2, column 3. Row 2, column 3 gave us 57. So that's going to be 57 minus open bracket, column total, where that 57 falls into. Of course, it's clear that is column 3, so the column total is 80. You can see the 80 there, then times chi-squared factor for that row 2 you are working on. And chi-squared factor there is 0.559. So square everything there you have in this bracket here, then divided by, just transfer what you have in the bracket down, because that down part is always column total times the chi-squared factor for the row you are solving. So that is that about the unmarkers beta epsilon chi-squared factor algorithm. Alright, it's a simple one, so you can just work on that. If you are done solving this, the row 1 term where I use black markers, you see I use different shades of marker to guide you. The black writing, all of them are for the summation in row 1. Then those in blue is when I was working with row 2. For the row 1, the summation is 29.4183. Then row 2, when I worked on it, is 23.5075. If you add these two together, the chi-square calculated will be 52.9258. That's the chi-square calculated. Quickly before I move on to the decision rule, I want to state this place. That what you have in the numerator here, alright, for row 1 in the numerator, take note, will be the same with what you have in row 2 for the first 10, where both of them share the same column total. Look at this. Where they share the same column total. You take now the first term with column total 98. Work this numerator on your own. Come to this guy with column total 98. Work the numerator on your own. You notice that the numerators will be the same. Which means if you actually know the value of this numerator, this part that have the same column total is the same numerator value you have here. The only difference that produces different results in the two is the denominator. Is that okay? The same thing here. The column total is 198. So it will correspond with the column total here for row 2. The numerators will be the same. So you can check it out yourself. Are you following? The numerators will be the same. What produces the difference in the value now is the denominator. Why I'm saying this is, if someone actually knows the value of these numerators, when working on row 2, you may choose to just copy the values you have here and put. Then take note, you want to be careful with the denominators, because the denominators will be different because of the chi-square factor for that row. Alright, now having obtained the chi-square calculated, what was the decision made? You can see the decision on the board here. we notice that chi-square calculated is greater than chi-square tabulated. And like we stated earlier, if chi-square calculated is greater than chi-square tabulated, we are going to reject the null hypothesis and then accept the what? The alternative hypothesis. And that, of course, that's what happened here. That's what happened. So the null hypothesis that stated that there is no significant difference in the opinion of the student, we will neglect it and accept alternative hypothesis H1 that said that there is a significant difference. It means that the students, all of them per se, generally did not agree, alright, that the excess rush in academic work should stop. And all of them did not say, okay, the rush should continue. Remember, we are not testing to hear from them whether, okay, let's say they should tell us, this group are saying it should stop, this it shouldn't stop, or whatever. What we are interested in is to know their opinion. It could be that they are saying it shouldn't continue. It could be that they are saying it should continue. All we know is that there is a difference in their response. There is what? A difference in their opinion. Some are for the view that it should continue. Others are for the view that it should not continue. But we don't know. We don't know. All we are sure of based on this is that, okay, their opinion differs. Alright, in our next video, we are going to see how we can use chi-square to carry out test of independence.